Welcome back. So we have the last talk of the day by Federico Ambrosino about exploring two-dimensional QCD with integrability. Please, Federico.
Okay, thanks a lot for the introduction. I would like to start by thanking the organizer for putting up this meeting. For me, it's an extreme pleasure to speak today because IGST was actually the very first meeting I attended back in 2021 when I was a bachelor student during COVID. So it meant a lot for me, so I hope it will continue to inspire other students. Today I would like to present some results based on this series of 2 papers I wrote with Shota. One came out on Christmas Day last year and the other one is out today on the archive, in which we explore an emergent integrability structure that underlies the meson spectrum in 2-dimensional QCD. And thanks to the talk by Kostya this morning, I don't have to spend too many words in motivating this work, as we have already seen how hard it is to compute anything at finite temperature in QCD, in real-life QCD. And unfortunately, the situation is not much better at 0 temperature, where we basically lack anything close to a full understanding of the analytical structure of confinement and how the mass gap is generated. And almost shamefully, still in the 21st century, we have to rely on toy models that at least have some of the feature that real-life QCD has, but is a much more controlled environment when we can hope to make some concrete computation statements. And we saw indeed an example this morning where the Gross Nouveau model is an amazing model that exhibits dynamical mass generation and chiral symmetry breaking, but in an environment in which we can do computation. But in general, in the last 5 to 6 years, there was a renaissance of these low-dimensional models. And today we continue in this spirit, but by revising probably the most famous model for confining gauge theory, that is the Toft model, that traces back to 74. There is nothing but a 2-dimensional version of QCD, and since 2D is not enough of a simplification, we also take the large n limit, in which the dynamics clearly simplifies, reducing to just ladder diagrams, just planar diagrams. And by this explicit simplification, we can have access to some emergent feature that would be very hard to analyze otherwise. And indeed, in this model, one can show explicitly that there are no free quarks in the spectrum, and illustrating the confining nature of the theory, and that spectrum, mesons organized in a discrete spectrum with Regge-like trajectory. And of course, there are some key differences compared to the real-life world, because gluons in 2D do not have any propagating degrees of freedom, so there are no glue balls and nothing like this, but still, this remains a very interesting toy model for mesons in confining theories. And now, since we want to talk about mesons, I cannot not mention the Bethe-Salpeter equation. That is our main tool to analyze their spectrum. And the Bethe-Salpeter equation is nothing but the statement that bound states arise from infinite resummation of one particle interaction between the constituents. So in a generic gauge theory, here you would put the one particle reducible kernel, and this equation would be very hard to solve. But in our model, in the Tuft model, in the large n limit, the rainbow ladder approximation is actually exact. So we can replace the very complicated 1p1 kernel with simple exchange of a gluon that in double line notation is this statement here. And since there are infinitely many interactions, this is a Bootstrap equation for the meson wave function and their mass. And this led Tuft, after some planar diagram algebra, to writing down this very famous equation that now takes his name. And this is nothing but an integral eigenproblem for 2 quantities, the meson wave function phi and the meson masses that here I call lambda. Please, it's not the coupling constant of n equal 4, it's just the mass of the mesons. It's such a similar problem to the spin of last week. And this is defined in a box, x in 0, 1, where x is nothing but the only dynamical quantity that is interesting in this model. There is the ratio between the light cone momenta of the 2 quarks. This is basically P, and this is R. And okay, there are no analytical solutions, unfortunately, but there is a very long study of numerical. There is a very long history of numerical studies of this problem, and I have to say that numerically solving this equation is quite tricky because of this double pole prescription here that makes it a very singular problem to solve. Especially boundary conditions are a bit tricky. But okay, anyway, one can extract some very nice properties of this spectrum already by numerical solution. For instance, asymptotically, the spectrum of this model is discrete. and actually organizes in rigid trajectory. We'll come back to this in a bit. I want to mention that the most important, in my opinion, after TUFT itself, most important paper in this realm was this paper by Fatev Lukyanov and Zamolodchikov that back in 2009 showed that if you take a particular limit in which you set the mass quarks, these are the quark masses, to the coupling constant of Young means up to a pi, okay? So this alpha coefficient is 0, then this equation can be recasted as a TQ system. And this motivated me and Shota to reconsider this very famous and old problem, because we thought it would have deserved a more thorough analytical studies in lieu of these results. And this is what we will do in this talk. Very good. So for simplicity, let me consider the single flavor case. So there's just one quark, or many quarks with the same mass if you want. And one of the key things is realizing that the correct space to study this problem is this mixed Mellin-Fourier space, in which one takes the Fourier transform with respect to the rapidity variable, because this maps the problem to minus infinity to infinity, and then one can Fourier transform. Because in this space, the TUFT equation, that was a very singular integral equation, becomes particularly nice in terms of analytical problem integral equation, and can be studied with more analytical techniques. So let's analyze it a bit. Let me call this right-hand side function f. This function f is very important. For instance, you see here is the measure of orthogonality between the wave function. One can show that since the left-hand side can be analytically continued, the right-hand side, at least in this strip minus 2i to I, the right-hand side is an entire function. So this f times I is an entire function. And for quark be massive, remember, maybe this I should write, this alpha was m squared pi over g minus 1. So when the masses are 0, this thing is minus 1. Then this equation gives rise to an Hilbert-Schmidt problem, for which one can prove that the solution will be normalizable on the real line and decay exponentially at infinity, and the spectrum is discrete and not generated. And now, remarkably, as we will see later, this can be analytically continuing alpha, because there's no problem anymore in analytically continuing alpha, while in the original problem, changing alpha changes the boundary condition of the box, so it's a bit of a tricky limit. In this case, alpha doesn't enter in the asymptotics. Very good. And now the key idea is to realize that if one considers this suitably defined Q function, then solution of the TUFT equation, psi n and lambda n on the discrete spectrum, are in one-to-one correspondent with the solution of a TQ-Baxter equation, where the transfer matrix is not polynomial, but it's a simple trigonometric part. The transfer matrix is Q plus this. Okay, and from the analyticity of psi, one can derive the analytical condition on Q. And again, Q will be entire, because this combination is entire in the strip and exposes at some particular place. And it grows lower than any exponential at infinity because of this cinch here. Okay. And in particular, we're going to derive this very important quantization condition. This will play a role soon. And now solutions under this analytical requirement exist only at lambda is equal to lambda n. For people that are a bit more familiar with integrability, the reduction from this problem to this is the Tracy-Widom kind of analysis. Very good. Now, this equation is not much simpler than the one we started with. Is an equation simultaneously for the Q function and lambda that is not much easier to solve. Yet in this problem, a truly important simplification happens, because if we add to the original integral equation an inhomogeneous term, now there is a space of two-dimensional space of inhomogeneity one can add, and this basis is particularly nice because it preserves all the analyticity that I listed before. Then after one add this inhomogeneous term, the solutions are no longer the solution corresponding to an eigenvalue problem, but it's an inhomogeneous problem. So solution will exist for any values of lambda in R upon just iterating this inhomogeneity together with the kernel. And then with this choice, the inhomogeneously extended Q function will satisfy the same TQ-Baxter equation, but at arbitrary values of lambda real. And again, for each lambda, you will have two solutions. So there's a Wronskian relating them. It's not too important to go into the technicalities. The most important thing is that they are subjected to the same analyticity and asymptotic condition. In particular, for people that are worried, the asymptotic behavior of Q does not depend on lambda. So the one of the extended problem is the same of the unextended one, but to a different quantization condition that we can derive explicitly. And this is particularly nice because now these Q plus and Q minus are much easier to compute than the original one. But yet we don't have any idea of how to go back to the original problem that we wanted to study. We wanted to study, in the end, the spectrum of 2th model. There's nothing to do at this level with the spectrum of 2th model. But again, this problem is very nice. And it's in the class of what Smirnov calls in a paper in French and in Russian, completely integrable kernels. Indeed, if one defines some spectral determinants that have to be regularized, this is not important, one can relate using the resolvent formalism ratio of them with the inhomogeneous Q function. And this gives us an amazing prescription to compute the eigenvalues, because this thing will have zeros at the position of the spectral levels. So we can reconstruct the spectrum from the inhomogeneous solutions. And this is an incredible simplification, because for 35 pages of this paper, the first paper, we derive a way to efficiently compute analytical expansion of this Q plus minus at lambda is equal infinity as an asymptotic series in 1 over lambda. And now here there's a lot of blah, blah, blah that it's not important to discuss today. The point is that after non-trivial things, one gets an expression for the spectral determinants of this form. And you might ask, how can you get from an asymptotic series in 1 over lambda cosine factor? And this is indeed, please read the paper if you're worried. But this has exactly all the features that we want. It's a function that has zeros at some points in the real plane, and we know that these zeros correspond to the spectrum. So it's very easy to see that when this guy is 2n plus 1, then this function will have zeros. And this is what we do here. We compute this function phi and xi explicitly. We set the xi to be this integer number, and we get an asymptotic expansion for the spectrum. Here I just write down this c, this is 0, this complicated constant, just to compare with WKB. And here I compare the analytical solution with the numerical one. And this, I want to remark, this is an asymptotic expansion of lambda infinity that works until like 0.5 here, or 0.6. So it's very remarkable. The still low value of lambda still reproduces the spectrum nicely. But it has very nice features. So first of all, at first order, kind of reproduce WKB. You see, WKB will say that 2 lambda n is n plus 3/4. This 2 lambda n is n plus 3/4. But you see that the explicit solution also produces a non-rigid term. This is quite interesting, I think. And it has also this very nice integral expression here that reproduces this singularity that alpha is equal to -1. And indeed, the alpha is equal to -1 point is a very important point, because there's the emergence of a massless mode in the spectrum that is associated with exact chiral symmetry. Here the story is a bit different compared to Gros Nouveau. Here exact chiral symmetry actually predicts the existence of a massless mode also at finite n. There are these papers that are very nice that discuss this thing explicitly. On top of giving this very nice asymptotic expansion for the spectrum, it also gives some very nice asymptotic expansion for the wave function. So it's a very effective method. And here I write down indeed, like for lambda n greater than -0.5, it reproduces the numerical values to 10 to the -6 already, only including terms up to 1 over lambda squared. So it's a very efficient technique. But now I want to discuss that one could have guessed that there's a massless mode here, not even by solving analytically the problem. Indeed, there's a very nice feature that I was saying before at the beginning, that this equation can be analytically continuous in alpha. And this gives us a lot of information, because psi, since the right-hand side is analytically continuable in the strip, will tell us that psi has poles whenever this function here that I was calling f has zeros. So studying the singularity of psi corresponds to studying the zeros of f in the complex plane. And here I plot in 3 different situations, and you already seen that something nice is happening to this critical point. So for positive masses of the quark, poles are not over the real line where we are integrating, so there are no problems. But as they approach the critical limit, they pinch the contour of integration in such a way that I cannot deform it in any way to avoid the singularity. So at the critical point, the integral equation develops a singularity, and indeed one can show that this wave function becomes delta function in this limit. And as I continue decreasing the mass of the quark, the wave function will have poles on the real axis, so they will not be normalizable anymore. But if one redefines them, it's still possible to have a discrete spectrum by going in the second sheet, as we will see in a moment. But okay, let's focus on this point. I want to analyze better this point, and in order to do this, analytically continue in alpha. And if I analytically continue, so here there's the new prime plane in the slides, while it's also useful to have in mind the alpha plane. There is this special point -1, and now I start with some point here and analytically continue around it. And as I analytically continue around it, I can study the monodromy of the roots of f. And this is very nice because, okay, they start moving, and at a certain point they cross the real axis. And when they cross the real axis, the integral eigenproblem will take some non-trivial residue contribution. And after a 2π rotation, you see that the eigenvalues, even though the alpha came back to the same point, the eigenproblem will have non-trivially changed. But if I do this 2 times, I come back to the original one. So this means that alpha 2 minus 1 is actually a square root branch point for the eigenvalues. And so this already predicts that lambda 0 of alpha will go like alpha plus 1. So what we learned from this very simple example is that a collision of root singularity are very special point in the spectrum. They correspond to critical points, at least from this very simple analysis. This can be shown using our analytical formulas in the very complicated integral in Z0. But as I was saying, one can study when it happens that in the complex plane there are collision of roots. And that point is not the unique one. As you can see here, there's another example, but there's another example here, and actually happens infinitely many times in the complex plane. And now all these points are not singular point in the first sheet, because nothing is happening here on the contour. These 2 roots decide to collide and nothing happens in their life. But in the second sheet, where I got a monodromy here, now they will become collision of roots points. And this predicts that, okay, one can show this, that at this special point in the complex plane, in the second sheet, these critical points become themselves branch point. And at this point, the m tangent value, only the even one, okay, turns to 0. And this is quite interesting because it seems to be a universal feature of confining theories. And for instance, the same happens in Ising field theory in a magnetic field, where this point is the Young-Lee edge singularity. And if one continues under the Young-Lee branch cut, finds infinitely many other critical points, at least in the Bethe-Salpeter approximation. And so this motivated us to just try to understand whether this is a particular feature of the 't Hooft model, of Ising field theory, if there's a more universal feature here appearing. And this motivated us to consider this generalized QCD. It's a very interesting model. So, and this is the subject of this paper of today. So in generalized QCD is a deformation that was introduced by Douglas Lee and Staudacher in the 90s. That basically amounts to replacing the kinetic term of the gluon by a BF interaction and couple it to fermions. So one couple an adjoint scalar field B with the field strength. And since a scalar field in 2D can be given any potential without spoiling renormalizability, we can actually take any potential for this. Now when the potential is B squared, one can integrate the B field and gets back QCD. But any potential works. And again, these theories can be analyzed very neatly in the large N limit. And we take for simplicity a polynomial potential. Many things can be generalized. And again, at large N, what one has to do is just studying the diagram produced by this new interaction. There are just some vertices for the gluon. And one can ask for which V of B this theory has a discrete spectrum of mesons. It's not even obvious that this theory has mesons anymore. It shouldn't be obvious. For some choices, this potential not even as minima. And if there is a discrete spectrum of mesons, are there critical points? Are the same of QCD? Are new critical points? This is the question that we address. And in order to do this, one has to resum again the one particle interaction. Before it was just ladder exchanges, right? In QCD. Change the ladder like this. But now you have this new interaction, so one has to resum all of them. And the result can be expressed nicely in the same Fourier space that we considered before. How much time do I have? I don't know. How much time do I have, more or less? Don't remember. Good, perfect. Perfect. So again, one can resum the Bethe-Salpeter equation, and the result of the resummation can be conveniently expressed in the same Fourier space that we used before. And now, one already noticed something nice. The left-hand side, the kernel that dictates more or less the analytical property didn't change compared to the one of 't Hooft model. The only thing that changes is the right-hand side, this function f. Now this function f will be different in general, and you see that the difference lies in 2 pieces. There's an effect, there's the production of effective quark mass that depends on the even part of the polynomial potential that we put here. We are the couplings of the polynomial potential. And there's a more complicated part that is encoding out the interaction between the quarks exchanged in this generalized way. But both of them can be computed in a closed form for any potential V of V. We have some closed expression in the paper, in which these coefficients, you see, they're also nice numbers. If you want, indeed, those are basically harmonic numbers. But also K of V can be computed in a closed form. And for instance, just to give a flavor, let's consider an example of a cubic potential. So this is a cubic potential. You see that now one of the coefficients is just a scale. It depends on 3 parameters, V3, V2, and alpha, but clearly one is just a scale, so one can set it to a number. And it's made of 2 pieces. The first piece is exactly the same thing of the 't Hooft model, this new cotangent hyperbolic, but there's a new correction that is indeed proportional to this cubic potential. And these trigonometric functions are just given by derivatives of this guy. So it's a very simple function to compute. The only complicated part are these coefficients, but okay, they can be computed. And now, remarkably, the same integral equation can be recasted, so this generalized QCD integral equation can be recasted again in a TQ-Baxter system, subjected to the same analyticity requirement as before. The only thing that changes is this transfer matrix piece, like here, but this is nothing, it's doing nothing but replacing this function f that we had before by a generalized function f. But this gives us a very nice recipe to study critical points and spectrum of the theory. This was very hard to do in X space. So these authors had a very nice semi-closed form for this Bethe-Salpeter equation, but it was very hard to study because, okay, this function here, if you imagine to take this weird transform back to X space, they're just crazy functions. There's no way to guess that this is the correct function to study in X space. And indeed, we can just study critical points by looking at points in this complex plane of f where we have collision of roots, exactly as in this case. And positive spectrum of meson will correspond to phases in this phase diagram where no singularity pinch the contour. So if we don't have any singularity on the contour, imagine here we have the contour. If we don't have any singularity, so if we have singularity, again, the wave function won't be normalizable, but one can still define. But anyway, in order to study this problem properly, one just needs to look for places in the phase space where these things don't appear. And remarkably, the inhomogeneous extension can be performed as before. So one modifies this integral equation adding the same inhomogeneous term, and everything goes through. And this leads to a very nice asymptotical analytical expansion for any V of B, both for the wave function and the eigenvalues. I will show you in a second. The point is that this is completely general. This can be done in a closed form for any potential and give us a very strong analytical imprint on how to study the phases of this very big class of theories. And here I want to give an example. So let's focus on the cubic potential. It's a very nice example that already has all the feature of the general case. So it's so in principle, one could look at 2 different phases. One in which one sets the this V3 coupling to be real. Classically, this doesn't have any minima. So there's no a priori reason why this model should have a discrete spectrum of meson if you want classically, but the quantum theory is somehow better. And studying the singularity in the complex plane of f dictates this phase space in which one is able to see where the critical points are. Those are this blue curve. And as before, those are square root branch cuts. And all the region in this space, alpha V3, that is shaded in the figure, is a region in which the spectrum of mesons is discrete and positive, and its criticality at the boundary. Again, at the boundary, one can just analytically continue in the second sheet, and in the second sheet, one of these higher mesons will become massless. So this is already nice. There were some preliminary results in this paper by Staudager, in which, but they had really to do numerics and try to understand what happens here. It is completely analytical. A nice thing, I found it very nice and amusing, honestly, is that one can also turn on an imaginary coupling for V3. Why is this the case? Well, because the B field, exactly as the gauge field, is odd under charge conjugation, or PT symmetry. And this is then therefore an example of a quantum field theory that enjoys, there is non-Hermitian, but enjoys PT symmetry. There is a sort of quantum field theory version of this Schrödinger equation problem studied by Bender. And indeed, even by putting a coupling to be imaginary, one preserves reality of the spectrum, because the eigenfunctions do not break spontaneously PT symmetry. Of course, then if you turn on some genetic V3, the spectrum will be complex because there is no PT symmetry anymore. But it's quite nice. And you have to keep this in mind for a second. One can also continue to imaginary values. Keep this in mind because now in these slides I want to show you that our analytical expansion work quite well also in this case. Those are the eigenfunction for some random values of V3. And again, one can derive some complicated asymptotic expansion. And again, it works quite well. Or this is already 1 over lambda. This is a 1 over lambda and already reproduces quite well the numerical results for some random values of decouplings. But okay. Now, as I told you before, opposite to the case of a 't Hooft model. So in 't Hooft model, what happened? That if one, let me write again this complex plane of alpha. So in the 't Hooft model, you had the complex plane of alpha that explicitly had a branch cut here. So in this region, so this is imaginary of alpha, this is real of alpha. Now, this region of the real axis corresponds to imaginary values of the quark masses, because m squared is less than 0, while this is m squared greater than 0. And there was no way to analytically continue to the m squared less than 1 branch without crossing the branch cut. You really needed to go through the branch cut in order to go to these values of the mass. Here, the situation is way nicer, because we also have the V3 coupling. And I showed you before that as you analytically continue at imaginary values of V3, the spectrum remains real. So if we want to access this very nice part of the complex plane to see what happens at those values of the mass, we can first analytically continue in V3, we go up, and then we go down again. So in this 3D plot, this region is the one where the spectrum was real. On the imaginary axis, the spectrum is real, and we see another line of critical points. This line of critical points is at negative values of the quark masses, some imaginary values of V3, but still has a discrete positive spectrum of meson. And quite interestingly, this line of critical points degenerates here in a very special point of the spectrum. This point of the spectrum, rather than being a critical point where 2 roots collide, in these critical points, 3 roots collide and pinch the contour simultaneously. And this is a very interesting point because it's a critical point in the spectrum associated with a cubic root branch cut, where 2 of the meson masses turn simultaneously to 0. And this is a quite interesting difference between this generalized model and 't Hooft model, as in the infrared, the theory flows to a different critical point. Here, the critical point is tricritical, while there was no way in the 't Hooft model to flow to a tricritical point. And again, one can play the same game, analytically continue, going to the second sheet and finding infinitely many other critical points. So there are, of course, there are infinitely many cuts, right? Because you can go through here, and you can go through here. But anyway, in each of these points corresponds to a special point in which there is a sheet where 2 of any mass of the quarks become simultaneously massless. And this generalizes to any potential. So if you give me a quartic potential, there will be a special point where the CFT is tetracritical. And I like this thing very much also because this phase space appeared recently in a paper by Mussardo and other people, I forgot to mention it here, in which they study again the tricritical version of Yang-Lee in the non-unitary regime. So all these points here when one's turned on an imaginary magnetic field are Yang-Lee singularity, and they degenerate in this tricritical Yang-Lee model. So this phase space is quite general of these 2D theories that have a confining potential. And this hinges to the fact that those critical points at finite NC will flow to some non-trivial CFT in the infrared that are still yet to be found. And indeed, I want to conclude by remarking some things. So I try to convince you today that the 't Hooft, the problem of meson in 't Hooft model reduces to solving a TQ-Baxter equation that in this case can be solved by the means of very nice analytical methods, and is very akin to analytical continuation. For instance, this is very similar to what happens in light ray. We learned last week from Simon that similar integral equation appear in that context, and the problem of analytically continue them is quite a non-trivial one. While in this specific case, this analytical continuation, rather than in the spin in alpha, can be performed in a very nice way. And one of the main points of this paper is that we uncover a very rich and novel structure of critical points that it's very interesting to speculate to what CFT they correspond at finite NC. A way, for instance, it could be studying WZW model. This is the bosonization of this QCD and their deformation. And now this critical points and multi-sheeted structure, as I was mentioning very often in this talk, seems to be a universal feature of 2D confining theories. For instance, even if you take a very simple confining theory, like what is the dumbest thing you can write? P1 square plus P2 square plus x1 minus x2. And you do WKB. You find that there are infinitely many masses. The first one is in the first sheet, and all the other n are in the second sheet. I mean, you know what I mean. They are behind the cut. So even the WKB of this very simple confining model exhibit this very nice structure. And a thing that I couldn't discuss today is that one can argue, okay, but maybe this is just an artifact of large N. And this could be the case, but we have, for this reason, explored a very nice model in which we fix NC to be 2. This was also done by Vadia recently for normal QCD April last year. And one instead takes fermions, rather than in the fundamental, in an arbitrary large representation of the gauge group. So this is some sort of large isospin limit. And also in this limit, there's a large charge limit in which there's a double scaling limit, in which one can again study the spectrum of meson, and one finds the same TQ-Baxter equation. Literally the same. Of course, there will be some slightly different coefficients scaled in the correct way with J, but still it's the same TQ-Baxter equation, so it really seems to be something universal in this model. Something akin could be tried to do for a joint QCD. It's a much richer theory, because in a joint QCD, the transverse polarization of the gluons are reproduced by the adjoint quarks. So this theory is more akin to IRD, because it also has transverse polarization for the gluons. And also in that case, if one studies the light cone Hamiltonian, maybe some techniques that we develop here could be applied. Now, something that I wanted to mention because of the paper of today is that one could also study the 't-Hooft Gross-Nouveau model, so adding a 4-fermion interaction. This was done by Zohar and company for a joint, but one can do it also for 't-Hooft. In our case, I mean, yeah, basically renormalizes the mass, so it's kind of not too complicated. A thing that I wanted to mention is that this model seems to be very, very nice in the context of bootstrapability, so I wanted to mention, because one can try to input the integrability spectrum into the S-matrix bootstrap problem. This is something that we are trying to do with Pedro and Gabriel, but on the other hand, one can try to compute the meson amplitude directly using integrability. So by computing convolution of Q function, it's something that I've been doing with Shota for a very long time. We should finish it. But okay, I think I'm good with time, so I can also stop here, and please ask questions.
Questions?
So these 2D theories, they are CFTs, right? The critical theories.
Yeah, because there is a massless meson, as you can see.
So what do we know about these CFTs? Do you know the dimensions, some dimensions, or can you do some formal bootstrap or put them in some plot? What can you extract out of all these CFTs?
Yeah, this is very hard. It's a very hard question. So what one would do in this to extract this dimension is put in the theory on finite volume. If you put the theory on finite volume, the dimension will be reproduced by just taking differences of this energy level. Now, this is something that I don't know how to do. What I can do is computing some sort of critical exponents, right? So if you want, these square root here are critical exponents. It's telling me what is the singularity when I approach criticality. And this is quite interesting to compare with Ising field theory, because if you put Ising field theory in a magnetic field, then you study the Bethe-Salpeter approximation, in which one expands around my basis of Majorana fermions. The Young-Lee fixed point is exactly modeled by a square root branch cut, also in this case. Now, in that case, one has the idea that as I add correction in 1 over mu square, one would approach the critical exponent of Young-Lee singularity. In this case, this would be an infinite series in NC. But one should really try to put correction in 1 over NC and see what happens. From here is very hard, I think, to... Yeah, so in principle, all these things could be different, I agree. So all this, the CFT here is supposed to be a U1 current algebra in the infrared for very generic feature described by Gomis and Affleck and Del Mastro in various papers. And it's very nice because indeed the current algebra, a U1 current algebra means that this thing is decoupled. There is indeed the decoupling of this pion in the infrared. And as whenever there is a CFT appearing exactly at the boundary between a PT broken phase and a PT symmetric phase, one should expect the CFT to be non-unitary. And indeed this is a kind of consequence of Coleman-Mermin-Wagner. I tell you, chiral symmetry breaking cannot be spontaneously broken in 2D, and if it is if it is the massless mode, it's non-unitary. So this is something very similar. But this CFT, in general, I expect to be non-unitary CFTs. Yeah.
So the Baxter equation is somehow reminiscent of this we found for the cusp.
Yeah.
Are there like any other parallels, or can you do this gluing of triangles stuff?
Yeah, here is a bit simpler than your case. It's much simpler. There's only a Q function, so there are no gluing condition if you want. It's a much simpler case because you have only one. The gluing kind of condition appears when you analytically extend. Here you have two. And you see this quantization condition have changed here. And this is very fine-tuned because why do we even put the singe here? We put it because if we put the singe, the analytical condition on Q remain the same. And notice this is not the same for psi, because psi, if now Q is not quantized to 0 at this special point, we'll have poles there. So there's something very non-trivial in the analytical structure of psi that is completely washed off at the level of Q. So I think in this case, your very non-trivial gluing condition is equivalent to really find the correct analytical extension of this problem by the inhomogeneous term. This is the equivalent. Yeah, for correlators, I mean, what we are doing with Shota is really being completely agnostic and studying correlation function directly from planar diagrams, or three-point function, something like this, right? And now each of these wave functions can be expressed as a Q function, and you can compute this as a convolution of Q function. And this is very similar to the cusp anomalous dimension. So this is something that, for instance, is in the paper of Cavalla and other people with you, in which you compute the cusp anomalous dimension as a convolution of 3Q function, and this measure appears, and then similar tricks appears also here. So there's kind of an akin structure. Yeah.
Other questions? Okay, I have a silly question. So you started from the Bethe-Salpeter equation for interaction of two partons exchanging particles,
yeah,
right? With these ladders. Do you have a spin chain picture underlying this story, even because you refer to light ray operators?
No.
So there, okay.
No,
I
don't have any spin chain kind of intuition in this case, I think, yeah.
So there couldn't be, your Baxter equation doesn't have a feature that is a number of sites,
no.
Or you couldn't do a similar problem for three particles interacting, for instance, like Pomerus versus Odder.
Right, this is an interesting question. Let me think. Because if you want the generalizing means as kind of these features, let me go to the things. Because you see the exchange is kind of multi-particles here. It's not really an interaction by different particles, it's an interaction by two particles with a generalized kernel that is a multi-point one. But no, I don't have a direct answer, right? Yeah.
Thank you. Other questions? So if there are no other questions, let's thank Federico again.